what is thinking itself? The process in our minds actually generated its own subtle magnetic field. Could we even measure that?
It sounds like science fiction, doesn't it?
It really does. Today, we're diving into some pretty cutting-edge mathematical frameworks trying to describe exactly that human magnetic fields, but going way beyond just basic biology.
Yeah, trying to connect the physical fields to our internal states.
Exactly. We've got some material outlining the sources, the math they're using, and this potential link to states of mind.
It's fascinating stuff.
Our mission here is really to unpack the core ideas. How are scientists even attempting to model something as, well, abstract as a thought using physics and math?
It starts really at the source. We have to figure out where these fields even come from.
Okay, so where do they start?
Well, the main contributors are neurons, individual nerve cells. You can think of them mathematically as tiny current dipoles.
Dipoles, like little magnets.
Sort of, but representing the flow of ions, electrical charge, across the neuron's membrane. It's an electrical thing causing a magnetic effect.
Gotcha. And how do they map this? It's not like you can see individual neurons firing easily.
Right. So they combine anatomical data, like from MRI scans that gives you the brain's layout, and then temporal data, the timing, from things like MEG or EEG. That shows when and roughly where the activity is happening.
Okay, so structure plus timing gives you a picture of the electrical currents.
Yeah, you piece it together. And it's not just the brain. The heart's electrical activity is actually much stronger, magnetically speaking.
Oh, right. MCG measures that.
Exactly. And even muscle activity, other cellular processes, they all contribute little bits to the overall field.
So, okay, we have these tiny electrical sources. How do you describe the magnetic fields they create with, mathematics?
Well, the absolute foundation is Maxwell's equations. They govern all electricity and magnetism.
The fundamental laws.
Yep. But for biology, things change relatively slowly compared to, say, radio waves. So we often use what's called the quasi-static approximation.
Quasi-static, meaning almost static.
Pretty much. It simplifies things, lets us focus on the direct link between the currents and the fields they produce almost instantaneously. We often calculate the field using something called the vector potential.
Okay. Still sounds complex.
Oh, it is, because these fields are constantly changing in space and time. You need the right coordinate systems and math to track it all.
And our body tissue itself must play a role, right? The fields aren't just traveling through empty space.
Absolutely crucial point. Tissue has conductivity, permittivity, electrical properties that affect how these fields spread.
Like resistance.
Kind of, yeah. And it's not uniform. Different tissues conduct differently. Muscle and white matter in the brain are even anisotropic. They conduct differently depending on the direction.
Wow, okay. So modeling that must be tough.
It requires serious computational power. Techniques like the boundary element method, BEM, or finite element method, FEM, are used to simulate how the fields interact with the complex shapes and properties of different tissues.
And this brings us back to measuring these incredibly faint fields. You mentioned MEG for the brain.
And MCG for the heart. Magnetoencephalography and magnetocardiography. They use super-sensitive detectors to pick up these tiny magnetic fluctuations outside the body.
All right, now for the really mind-bending part. Can we actually link these fields to thoughts?
Okay, deep breath here. This is highly speculative, venturing into new territory.
Understood. But what's the idea?
One concept borrows a bit from quantum mechanics, the idea of a state vector. Imagine representing a thought not as one thing, but as a complex pattern across the brain, a high-dimensional vector based on neural activity.
A thought vector.
Sort of. And the really radical idea is, could that state, that specific pattern of thought, have its own distinct electromagnetic imprint, its own field signature?
Whoa. So thinking apple might have a different magnetic pattern than thinking banana.
Yeah.
Metaphorically speaking.
That's the extreme end of the hypothesis, yes. The framework suggests that things like attention, intention, the content of thought, might actually modulate the underlying neural activity.
Modulate how? Like turning the volume up or down?
Kind of. It could influence the effective strength, the dipole moment, of neurons or whole groups of neurons. There's even math trying to capture this, like a modulation function based on thought, attention, and intention influencing the source term.
So the thought itself changes the source generating the field.
That's the proposition. Maybe the total field we measure is the background brain activity plus an extra component directly related to the ongoing thought process.
How would you even write that down mathematically?
They use the Biot-Savart law, which connects currents to magnetic fields, but they modify the current term, J Shannon, or the dipole moment, pp, to include this modulation factor, let's call it lambda, that depends on the thought state.
So B equals something times current, but the current is now thought influenced.
In essence, yes. It's trying to mathematically embed the mental state into the physical equation.
Could different types of thoughts show up differently, maybe in frequency?
That's another angle being explored. Could specific thought states correlate with power in certain frequency bands of the magnetic field? Think alpha waves, gamma waves, but maybe linked more directly to cognitive content. And then there's the idea of nonlinear dynamics. Maybe small fluctuations in thought patterns could, through some complex brain dynamics, get amplified into larger, measurable changes in the electromagnetic field.
Okay, this sounds incredibly ambitious. What are the biggest hurdles?
Oh, huge hurdles. First, proving any definitive mathematical link between a specific thought and a specific field change is, well, monumental.
Yeah, I can imagine.
Second, these fields are unbelievably weak. We're talking femtoteslas, picoteslas. Measuring them accurately and filtering out noise is a massive challenge.
Right. The signal is tiny.
And fundamentally, we're trying to mesh consciousness, subjective experience, with the objective laws of physics. That's a deep problem.
So wrapping this up, what we're seeing is scientists building these really sophisticated mathematical models. They're trying to connect the dots between neurons firing, the magnetic fields produced, and maybe, just maybe, our internal mental states.
Exactly. It's a bold attempt to find a physical description, however subtle, for processes we usually consider purely mental.
It definitely gives you a lot to think about. Imagine for a moment, what if we could decode the electromagnetic signature of thought? What could that mean for understanding consciousness or communication or even new technologies? What other questions does this raise for you about just how interconnected our minds and the physical world might be?